Okay, we're back for part 2 of point 6 trigonometric function example problems. And in the previous video, we went through example 1, finding arc length. Example 2, confirming that cosine and sine are even and odd, respectively. Example 3, finding trigonometric values given one value, in this case the sine and tangent being less than 0. Okay. Example 4, graphing a trigonometric function with translations. Example 5 is where we left off, and it has to do with frequency of a musical note. So I did put a little link in there for you guys to review if you're interested in the physics of the harmonic waves caused by the tuning fork. So this problem, a computer analyzes the pressure displacement versus time for a wave produced by a tuning fork and gives its equation as y is equal to 0.6 sine of the quantity 2488.6 x minus 2.832 plus 0.266. Estimate the frequency of the note produced by the tuning fork. So the first thing I'm going to do is factor out the b so that I get this expression. So you can kind of see, again, with the factoring of the b, factoring out the b, 2,488.6, we divide each term in the grouping by 2,488.6, which gives us x minus 2.832 over 2,488.6, and then the plus 0.266 is on the outside. So what we want to do here is we want to just find out what the frequency is. And as it turns out, the frequency, first you know the period is 2 pi over the b value. The frequency is then the reciprocal of the period, so it's going to be 1 cycle per unit of time. So, and I'm not going to get into the science of it, but I will talk a little bit about units here. So if we have the period then is 2 pi, and that's going to be over 2,488.6, like so. I'm not really going to worry about that number because I'm going to take the frequency and then I'm going to say, well, that's the reciprocal 1 over the 2 pi over 2,488.6. So when I divide that out, well, let me just rewrite this. This is going to be 2,488.6, and that will be over 2 pi. Looks like I got a frequency of about 396. Now I want you to think about this. As a sine wave goes, you know, it's going up top here. It's going like that. So you go through a complete cycle from like here to, where do we get back? Up, down, up. So we get through a complete cycle when we've gone through kind of like a mountain and a molehill. So we have 396, and we often call this hertz, but I'm just going to say it's cycles per unit of time. Now, sometimes we're talking about frequency, we talk about the distance the wave goes per unit of time, like in meters per second. But in this case, I'm just going to say cycles per time. So if you watch the video, the science video that I have, I think it's abbreviated HZ is hertz. So it's a unit of measurement for waving, for measuring frequencies. Okay, so your answer is 3. The frequency would then be 396 cycles per unit of time then. Okay. The next example is on restricting the domain of the sine function. So show that the sine function, sine goes from negative pi over 2 to pi over 2. Show that it's 1 to 1 and graph its inverse. So this is really the easiest way to graph the inverse. If you have a sine function already, just switching the x and y values. So you recall that sine, we only want it to go from, try my best to do this, so where you have pi over 2 here and 1, and then you have negative pi over 2 and negative 1 here on the other end. So we're just going to flip these points that you see, and you see a table down below, and we're going to create a table see the table below, for the sine inverse. So notice we use the capitals. Very often we use capital letters to designate the principal values for these inverse functions. So this function is going to go like this. You can kind of see the line. I've placed the line y is equal to x in here as well, where this is a sine inverse, and then the sine, and then here's the sine inverse over here, and the line y is equal to x. So you can see that we have the point 1 pi over 2. Okay, and then down here, I have -1 is the x value and negative pi over 2. So really just a switching of the x and y's. Okay, so I'll let you look at that again. Play around with your graphing calculator and go for these functions on the graphing calculator and see if you can designate your angles as being in degrees so you can understand the angles a little better and see if that makes a difference. All right, next example is finding angles in degrees and radians. So for this one, we want to use the calculator mode. We want to have it in degrees so we can see what our answer is in terms of an angle. So you're going to use these steps that you see here, second, cosine, and then we're going to use the plus or minus to put in the 0.5, and then enter. I think we might need a parenthesis for this parenthesis as well. So here we go. I'm going to step over to the cal. I think I already have it in there, so I'm going to hit second cosine, so you get that, and I'll hit the negative and then the 0.5, close it back up again, and then I get 2.09. So now if you recognize I'm in radians, so I'm going to change the mode to degree mode. And then I'm going to go back to the screen. I'm going to hit second enter to bring the expression back up. And you see I get 120 for my answer. Okay, so the answer there is 20. And that's in degrees. So remember, see I have that second parenthesis highlighted. You probably should use that. Okay, and now I want to change this to radians. I have a slight problem here. I need to just erase this because I'm going to change to radians, and I have 120 degrees, and I need to multiply that by pi over 180 degrees. Okay, so I'm going to simplify that because the 120 and 180 have a common factor of 60. So this becomes 2, and so we get our answer of 2 pi over 3. Now, if you saw the decimal value that I had on the screen, that decimal value is 2.09, Just now, if you get if your calculator's in radians, that's what you're going to get. That you might not understand as much, but you can do it like that. So remember when we multiply by this pi over 180, that's like multiplying by 1. It's just like 12 inches over 1 foot has a value of 1 as a ratio because they're equal, the units equal each other. 12 inches is equal to 1 foot. So the same thing with pi over 180 degrees. All right, and then the last thing here is just putting the answer. So it's 120 degrees or 2 pi over 3. And we usually leave the radians out there. Okay, and then this last problem, using inverse trigonometric functions. So we want to think for just a second when we're solving for x. X at this turn is the angle. So I'm not going to put an x on the x-axis in the coordinate system, but I am going to use the coordinate system for this. Notice I'm labeling the angles x1, here's the x1 over here, and then I'm labeling x2. Okay, now here's the question. How do I know where my angles are going to terminate? If down below, if you look at the little note I have, x is the angle. X is the angle, and 0.7 is a positive ratio. Sine is positive in quadrant 1 and 2, so that's why I know the angles are going to terminate in quadrant 1 or 2. And it's not a 1 or a 0, so it's not on the axis, so I'm just drawing it like any old angle there. So sine x is equal to 0.7, and then when I put that into a calculator, sine inverse, so if I hit, skip that for now. So if I hit second, let's check the mode, make sure that we're in the right mode. I'm in radian mode. So I'm going to leave it in radian mode, and I'm going to hit second quit, second sign, and I'm going to type in 0.7, 0.7. Close up the parenthesis, and I get this number, 0.77539. So I get this number. Okay, here we go. All right, now, that doesn't really give us the whole answer here because I want both angles. So what I'm going to do is try to recognize that this angle is congruent with x1. So this is the same angle. So all I have to do to find the other angle, I know x1 is equal to 0.77539. And x2, think about this for a second. If these two angles are congruent, then x2 is just going to be pi minus 0.77539, approximately, because again, we're working with decimals, okay? All right, so remember when you're doing this inverse notation that your input is the ratio and your output is the angle. So your answers here are the angles. Now, it might seem a little weird at first when you're dealing with decimal angles, but I like to do that because sometimes students get so used to having pi in the answer when you're dealing with radians, and then they get a decimal and there's no degree on it, and they have to recognize it as such that it is in radians. All right, so here's the next one. So now we have tangent x is equal to -2 in the second one. And so I'm going to hit tan inverse of -2, and I'm going to get this answer. But remember, that is one of the answers, or it could be one of the answers. In this case, it is. So I have to check it out. That's going to give me a quadrant 4 angle. And if you look at tangent, -2 is negative. So it's a negative ratio. So I'm in quadrant 2 and 4. The two quadrants you see, that's where your angles are going to terminate. So now with that, now I have to figure out what the other one is. Now think, they're pi away, right? So I can actually take the first angle and I can just say, all right, well, here's x sub 1. X sub 1 is equal to -1.107. That's the first angle. And then you have to think about how far you are away. So if I go this way, that's pi units. Let me use a gold. This is pi units. That angle is pi. So what I'm going to do is I'm going to take my original angle for x sub 2, and that's going to equal -1.107 plus, and I'm going to leave a little space. I'm going to put pi, right? But if I put pi on there, I already have listed, and that's going to give me x sub 2, right? It's going to be 1x sub 2. But then, think about this for a second. How about if we just say k times pi, and then that's going to bring me back each time where k is an element of the integers. So think about this for a second. That'll bring me back here, right? And k could be 0, so that'll take care of the first one too. So we actually don't need to list x sub 1. And we could just state our solution. All of the solutions would be of this form. So if you notice that we were on a different kind of setup here. The first one, we had an interval from 0 to 2 pi. Those are my only two answers. But for this one, we go from negative infinity to infinity. So we have an infinite set of answers there. It's just going to keep on going. Every time I add pi, I'm going to be back at the other angle from quadrant 4 to quadrant 2. Okay? From 2 to 4, to 2 to 4, and it just keeps going around. Okay? So this, we write it like this, or we write our answer like this because your answers can vary. Okay? So that's example 8. That'll be the finishing of this extra trig function examples. And with that, that completes our videos for 0.6 and the finish of our Unit 0 on pre-calculus review. So I will see you when I see you. Have a great day. Keep looking up.